So now we continue to get into what the bonding of specifically carbon looks like. Now what we're going to go over here applies to other atoms as well and is a review of something that you learned in general chemistry, but we want to get into it a little bit differently here just to show how it applies to what we're doing in organic chemistry. And the main point here is hybridization. So if we think about the electron configuration for carbon, we get 1s2, 2s2, 2p2. And if we draw out an orbital diagram for that, it looks like this. The two electrons in the 1s orbital are paired. We pair the 2 and the 2s, and then the 2p will end up with two unpaired electrons. And so what this would suggest to us is that this would allow for two bonds to form, even though we know that carbon needs 4 bonds. Why 2 bonds? Well, we only have the 2 unpaired electrons, and so those are the ones that would want to form bonds. So what if we went to 4 unpaired electrons? It would look something like that. The problem here is this is not stable. Why not? Well, it's not the ground state. This is an excited state. Because in order to get here, we had to take one of these lower energy 2s electrons and promote it to a 2p, a higher energy state. There's also a second problem with doing this. If we look at methane, which is the simplest organic molecule that we have, carbon with 4 hydrogens, we find all 4 CH bonds are equivalent. Now, if we use that excited state configuration that we had on the previous page, which I'll redraw here, that would not account for 4 equivalent bonds. And the reason for that is what it would mean is that one of the bonds was forming with a 2s orbital, or an electron from a 2s orbital, and the other 3 were forming from electrons in 2p orbitals. And given that we know that there's a difference between s and p orbitals, that wouldn't allow us to account for what's going on here. So what's really going on? Well, that's where hybridization comes into play. And so hybridization was first proposed by Linus Pauling. Now, Linus Pauling was very, very interesting if we look into his career and life in terms of what he did and everything else. Why do I say that? Well, Pauling, first of all, is the only person to ever win 2 unshared Nobel Prizes. He won one in chemistry, and then a number of years later, he actually won a Nobel Peace Prize. And both of those were solo prizes. So no one's ever done that, either before or since. There have been others who have won 2 Nobel Prizes, but never 2 unshared Nobel Prizes. But later on in life, Pauling ended up promoting pseudoscience. And Pauling became a major proponent of a theory that we now know just is pretty useless, and the idea of taking megavitamins. So it's very interesting that someone like Pauling, early in his career did so much important and really interesting work, and then as he got older, ended up in an area that just worked against science. But what does our hybridization propose? Well, for a molecule such as methane, and hopefully we remember our bond geometries, methane is tetrahedral. But what happens is that 2s orbital, there's one of those, it combines with the 3 2p orbitals. Now, anytime we add orbitals together, we have to have conservation of orbitals. In other words, if we start with 4 orbitals, we have to end with 4 orbitals. So when this 2s orbital combines with the 3 2p orbitals, we're going to get 4 new orbitals. And we call those sp3 because they are 25% s and 75% p. And so that leads us to our typical carbon with 4 single bonds. It's tetrahedral with bond angles of 109.5 degrees. And in fact, if you recall from general chemistry when you learned about bond geometry and electron domains, in general, if we have 4 electron domains, whether that's 4 bonds, 3 bonds, and 1 lone pair like we often see for nitrogen, for example in ammonia, or 2 bonds and 2 lone pairs like we might see in water, these are always, or I should say almost always, going to be sp3. Right, now what about as the number of electron domains changes, or we start adding pi bonds? So what about 3 electron domains? And we might see that in a molecule such as ethylene, where the carbon has a double bond, so it's 3 electron domains and no lone pairs. Well, recall that pi bonds are formed from unhybridized p orbitals. So now there's one 2s orbital available along with 2 2p orbitals, and that gives us our 3 sp2 orbitals. So carbons with 1 pi bond are sp2 hybridized, and they have trigonal planar geometry. And so sp2 atoms could include carbon bonded to 3 atoms, nitrogen bonded to 2 atoms, or an oxygen bonded to 1 atom. All of these have 1 pi bond. Now, it's not necessary to have a pi bond in order to be sp2 hybridized, but it is necessary for the molecule to be bonded to 3 other atoms, or have 3 electron domains. So boron, for example, you may recall that group 13, which contains boron, is an exception to the octet rule. And so boron is typically happy forming 3 bonds. And this is something that will become relevant to us later on in this course. We'll actually see that boron does some very interesting organic reactions because of this property. But boron, when it's neutral, has 3 bonds and no lone pairs, which fits us into this 3 electron domain category, and it's also sp2. All right, finally, if we go down to 2 electron domains, so this would be a carbon or nitrogen with 2 pi bonds. This generally doesn't apply to oxygen at all. So most commonly this would be a carbon with a triple bond. But it could also be a carbon that has 2 double bonds. So we're talking here about this central carbon. This could also be a nitrogen that has a triple bond. In each of these cases, we're using 2 p orbitals to form pi bonds. So we only have one 2s of orbital, and one 2p orbital available. So we form 2 sp orbitals, and that leads us to a linear geometry with bond angles of 180 degrees. So sort of our take-home message here, and what we really want to be aware of, is especially for carbon. For carbon, 0 pi bonds, and these are all neutral carbons. When we start looking at anions later, there will be some small differences, but turns out they're not terribly significant. So if we have 0 pi bonds for carbon, then it's sp3 and tetrahedral. If the carbon has 1 pi bond, it's sp2 or trigonal planar. And if it has 2 pi bonds, then it's sp and linear. So now you should get out in-class exercise number 3, which deals with hybridization, and start working through some of those examples.